Unit 4 Chemistry, Chapter 12, Part 3. Still looking at NMR, but now we are looking at NMR involving hydrogens. It's called proton NMR, but remember, if we're looking at a hydrogen, its nucleus is just one proton. Okay, so same thing, just two different terms for it. Just as with carbon NMR, what we're doing is changing the spin. Just as with carbon NMR, it's going to tell us about the environments, but now we're looking at hydrogen environments rather than carbon ones. Also, just like with carbon NMR, we're going to look at three main features. How many peaks there are, because that's now going to tell us how many hydrogen environments we've got. The area under each peak, because that's going to tell us the ratio of hydrogens in those environments, whether there's the same number in each or different. And then thirdly and finally, and almost never, the chemical shift. Okay, so if we looked at something like propanone, okay, also sometimes known as acetone, used in nail polish remover, okay, we can see that we've got 3 carbons here and 3 carbons there. But if we hydrogens, 3 hydrogens there, 3 hydrogens there. If we look at the structure, we can see this is entirely symmetrical. So they're both bonded to the same internal molecule, internal carbon, which is bonded to an oxygen. That means they're in the same environment. So for this, we'd only expect one peak, which is what we see. Okay? One peak for all of those CH3 protons, which are bonded to this C double bond O in the middle. And of course our TMS. Still have the TMS standard. Okay? If we looked at something different though, this here is dimethoxymethane. Okay? What we've got in here, as you can see, are a couple of ether groups. Okay? We don't need to worry about naming that, just we might see it, we might need to identify it. Now here, we've got this one and this one. Now they're the same as each other, yeah? But this one in the middle is different, and it's different because it's attached to a carbon which is bonded to 2 oxygen groups, whereas here, they're only bonded to 1 oxygen, okay? So here we're going to see 2 different peaks, okay? This is our CH3, that's our CH2. We're also going to start to see our ratio, okay? We're going to see that we've got 1, 2, 3, 4, 5, 6 in total hydrogens in a CH3 environment, and 2 in a CH2, okay? So we've got a 6 to 2 ratio, which is a 3 to 1 ratio, and we can see that this is basically 3 times higher than that. Quite often on a question they'll write that ratio above for you or give it in a table, okay? But you could measure it, and as long as we're getting a whole number ratio, it has to be a whole number ratio, so you might be doing some rounding off to make sure you're getting there. Okay? In something like ethanol, we've got 3 different hydrogen environments. We've got this CH3, there are those 3 hydrogens there, which is going to give us this peak here. Okay? And notice here that this is a more spread out peak. Sometimes you see it like that. Okay, we've also got the CH2, and we've also got an OH. So we've got 3 in a 3 to 2 to 1 ratio. Okay. Notice in all of these I'm not using the chemical shift, because again, my chemical shift is likely to steer me wrong. Okay. If I don't have to use the chemical shift, I'm not going to. Okay. So my area under the peak, and it is the area under the peak rather than specifically the height, but the height can approximate it. That tells us the number of environments in each environment, number of hydrogens in each of these environments. Okay. The chemical shift is due to the spinning electrons that are around the nuclei making their own magnetic field, and that shields the nuclei from our external magnetic field that we're putting in. So the more shielding, meaning the more electrons circling them, the lower the frequency for them to be moving from parallel to antiparallel. So basically, the lower the number of the chemical shift. Okay? That's why we get these differences. Okay? If we are bonding hydrogens to an electronegative element, normally via a carbon, then remember those electronegatives, like oxygen, are going to steal more than their fair share of those electrons, which means that is going to reduce the electrons orbiting those hydrogens. which means it is going to increase our chemical shift. Okay, so you will see that the lowest ones are where we've just got carbons and hydrogens. And remember, R means we've just got a hydrocarbon chain on the either side. Okay, if we start adding in oxygens, but they're a little bit farther away, then we get a increased chemical shift. The closer those oxygen gets, the higher it gets. And if we start adding a couple of oxygens, then we're getting a very high chemical shift, because that means this poor little hydrogen's got almost no electrons around it, so almost no shielding, so it's having to deal with the full force of that magnetic field.